Let's now calculate the temporal complexity of a program. Let's take the program Pascal of n, the function which calculates the nth row of Pascal's triangle. So it takes a natural number n and returns the nth row, and each row is represented by a list of integers. So that the 0th row is 1, the first row is 1, 1, the second row is 1, 2, 1, and so on. So one way to define this nth row is as the expansion of a plus b to the n. So we take this binomial, we expand it, and all the coefficients in the expansion, they give a row of Pascal's triangle. So a plus b to the third will give me the third row of Pascal's triangle. So here's an algorithm to compute Pascal of n. So first of all, for row 0, I return the list containing a single element, 1. For row n greater than 0, I first calculate Pascal's triangle for row n minus 1. I shift it left, putting a 0 at the right. I shift it right, putting a 0 at the left. And then I add them pairwise to get row n. So here, for example, I take row 3. I shift it left, putting a 0 at the right. I shift it right, putting a 0 at the left. And then add pairwise, getting 1, 4, 6, 4, 1, which is the fourth row. So here's the source code for this program. So it's recursive. If n is 0, then I return the list containing just 1. Otherwise, I call Pascal n minus 1. And each time I call Pascal n minus 1, I give it the shift left. I give it also the shift right. And then I do an add list. So here at the right, I have a graphical representation. So the n comes in at the top. It's given to both Pascal n minus 1 calls. So I do subtraction by 1, and then I call Pascal. The result goes to shift left and shift right. The result of shift left and shift right goes to add list, and the final result is the output. So we need 3 auxiliary functions. So shift left puts the 0 at the right. So the only way to do this in the functional paradigm is to traverse the list all the way down and create a new list with a 0 at the right. So that's what we do. Shift right is simpler. We just put a 0 at the left. And then there's the function add list, which traverses in a synchronous way through L1 and L2, getting the elements pairwise and adding them and returning the list of their sum. So let's calculate now the temporal complexity. In order to do that, we're going to use a simple analysis where we want to count the number of calls of Pascal that is done in a complete computation. So for Pascal n, we have 2 calls of Pascal n minus 1. So we have here a simplified analysis. Pascal n does 2 calls of Pascal n minus 1 if n is greater than 0. And this gives a total of 4 calls of Pascal n minus 2, because Pascal n minus 1, each of them calls Pascal n minus 2 twice. And if we go down, finally, we get 2 to the n calls of Pascal 0. Notice I have not taken into account the time of execution of add list, shift left, and shift right. You can do this in a more sophisticated analysis, and you will notice it does not change the result. So we add all these calls up, 1 plus 2 squared up to 2 to the n. This gives us O of 2 to the n. This is in fact the tightest, best bound. We can't find any function smaller than 2 to the n. So this is exponential. Let's see if we can do better than that. In fact, we can do much better. We can get by with just 1 recursive call instead of 2 if we keep the result in a local identifier L. So we have L declared here. L is equal to Pascal n minus 1. And then we do the shift left, shift right, giving L as an argument to both. The complexity is now much different. It's proportional to n here because of the time of execution of add list, shift left, and shift right. And it's n minus 1 then for the recursive call n minus 1, n minus 2, and so on down to 1. So if we add all these numbers, we get O of n squared. This is much, much better. With fast Pascal, we can in fact calculate very, very big rows of Pascal's triangle in very reasonable time. So I recommend you try it and see how much faster it is than Pascal.